Hi everyone, thank you so much for coming to this video. So today we're going to be going over the second derivative and some of its applications. So reviewing the lessons that we did on differentiation and also stationary points will be really useful as we're going to be using that in this video. So the learning objectives for today is to be able to understand and use the second derivative and to be able to use the second derivative with concave and convex graphs and points of inflection. So after going through all of this, we're going to be doing some exam style questions to see how you can apply this. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to. But let's get started. So if we move to the first learning objective, understand and use the second derivative. So the second derivative is just if you differentiate a function twice. So it is measuring the rate of change. So if you want to measure the gradient of a graph, you differentiate that firstly. Then if you want to measure what the rate of change of the gradient is, you have to find the second derivative. So to do that, the first thing you want to do is you just want to find the first derivative, so f dash x. So if you do that, that'll just be equal to 6x squared. And then to find the second derivative, you just write f dash dash, and you just differentiate your first derivative. So you just differentiate 6x squared, and you would just get 12x. So another way you could write this is if you have y is equal to 2x cubed. So if you do dy of dx first, you just get 6x squared. Then if you do d squared y over dx squared, so that's another form of writing your second derivative. One way is f dash dash x, and the other way d squared y over dx squared. So you just differentiate this again, and you would get 12x. So that's just an overview of what the second derivative is. It's just differentiating a function twice. So you differentiate it once to find your first derivative, and then you differentiate your first derivative to find your second derivative. And this using the second derivative has loads of applications with concave and convex graphs and also points of inflection. So now that we've understood what the second derivative is, let's move on to the second learning objective. So moving on to convex and concave graphs, I've written the two out here, so let's go through them individually. So for the first one, convex graphs, these are ones that curve downwards. So as you can see, it's like a happy face. It curves downwards like this. And if you have a straight line joining any point, 2 points, this line will be above the curve. So let's say you have 1 point here and 1 point here, and if you draw a straight line joining the two, then you can see that that's above the curve. And then as you can see, for this graph, a graph will be concave if you have your second derivative is greater than 0. So that means your gradient of the curve is just increasing as your x values get larger. So if you remember that a gradient is the same as if you have the gradient of your tangent of the graph. So if you draw some tangents, so you say, let's say this is one tangent like this, another one would be like this, and another one would be like this. So as you can see, your tangents are getting steeper and steeper and steeper as you increase your x values and go up the curve. So that just means that your gradient is also increasing as you increase your values of x. So that's just the same as saying your second derivative is greater than 0. Your gradient, the rate of change of your gradient is increasing. So the next curve we have are concave graphs, and these are curves that curve upwards. So it's kind of like a frowny face. It curves up, and then if you join any 2 points on the graph, on the curve, your line would be below the curve. So let's say we join this point and this point. If you draw the line connecting it, you'd see that this is below your curve. And then the last important property relating to second derivative is that if you have if you do the second derivative, that would always be less than 0. So this means that your gradient of the curve is decreasing. And you can see that if we draw some tangents of the graph, if we have one like this, then we have another one would be like this, another one would be like this. And as if you can see, the our tangents are getting flatter and flatter. So if we continue, it go like this, like this. So as you can see, our tangents becoming flatter and flatter. So that just means that the gradient of your curve is decreasing. Your rate of change of your gradient is decreasing. So the key takeaways from this relating to second derivatives and convex and concave graphs is that if you have your second derivative is more than 0, then this means you have a convex, your graph is convex, or the parts where your second derivative is greater, then you have your convex, your graph at that point would be convex. And then if you have your second derivative is less than 0, then for those parts of your curve where that happens, when your second derivative is less than 0, then on those parts you have a concave graph. So now we've done concave and convex graphs, let's just go over an exam style question to see if you've understood this. So you have an exam question here. Feel free to pause the video and try it out for yourself. So we want to find the range of x values for which the graph y equals 2x cubed minus x squared plus 5 is concave. So to do this, we first want to find what the second derivative of this curve is. So first, we just want to do dy over dx, so the first derivative. So if you do that, that would be equal to 6x squared minus 2x, and then that's it. If you differentiate a constant, you just get 0. And now if you want to do the second derivative, so d2y over dx squared, we just want to differentiate our first derivative, so we could get that is equal to 12x minus 2. And we want to find the range of values for which the graph is concave. So if you go here, that's when your second derivative is less than 0. So you want to find the values when this is less than 0. So then if we rearrange to find this inequality, we would get 12x will be less than 2, which means that x is less than 6. So that means that the range of values for which the graph is concave is just when x is less than 6. So now that we've done a question example for the concave and convexity, let's move on to points of inflection. Okay, so moving on to points of inflection. So points of inflection is just points when the curve changes between being convex and concave. And in general, most of the time, a point of inflection occurs when your second derivative of x is just equal to 0. So for example, if we have this graph, which is fx is equal to x cubed minus 6x squared plus 9x plus 1, our inflection point would be a point over here, because as we go from there, here our graph is concave, but then as we move to down here, our graph becomes convex. So that's why this is point of inflection. And if we were to find this point, first we just want to take the first derivative of x. So that would just be equal to 3x squared minus 12x plus 9. And now if we were to take our second derivative, that would just be equal to 6x minus 12. And we know that a point of inflection occurs when our second derivative is equal to 0. So then if we solve this, we'd get 6x is equal to 12. So then our x is equal to 2. So our point of inflection here is when our x is equal to 2. And if we were to just check that this is a point of inflection, we want to work out what the second derivative does when x is less than 2 and when x is greater than 2. So when x is less than 2, let's say if our x is 1, for example, then we know that f dash of 1 is just equal to 6 minus 12, so that's just minus 6. So our f dash of x will be less than 0. So that means at this point, our graph will be concave. And then for values of x when x is greater than 2, so let's say when x is equal to 3, then our second derivative would just be equal to 6 times 3, 18 minus 12, so that should be 6. So that means our second derivative is greater than 0. So that means for values above 2, our curve will be convex. And for values below 2, our graph is concave. So that means when x equals 2, our graph switches. So then this point is called our inflection point. But you've got to be really careful, because not all graphs where your second derivative is equal to 0, for all graphs, that point is not necessarily an inflection point. So for example, if we have f of x is equal to x, if we do the first derivative, that would just be equal to 1, and our second derivative of x, that would just be equal to 0. So you have our second derivative is equal to 0, and this would happen for all values of x. But our graph is just a straight line. It's not switching between convexity or concavity. So that means that over here we don't have a point of inflection, even though we have that our second derivative is equal to 0. And similarly for this graph, f of x is equal to x to the power of 4. If you were to do the first derivative, you would get 4x cubed, and then if you were to do the second derivative, you would get 12x squared, and when that is equal to 0, that's when x is equal to 0, so at this point here. But as you can tell, our f dash x, that would be greater than, our f of x would just be greater than 0 for all other points of x rather than 0. So that means that for all values of x apart from 0, our graph is just will just be convex. So you don't have, for values of x below 0 is concave or convex, and then for values above it's the other. You just have it's convex for all values of x. So you've got to be really careful that your point of inflection is only when your graph switches between convex to concave or from concave to convex, like this one. So you have to check on both sides of what you get as your inflection point when you set your second derivative equals to 0, whether below you have your second derivative less than 0 or more than 0, and then for above 0 you have your opposite. So if you have below 0, if you have your second derivative below 0 for values of x below your inflection, then for values of x above your inflection point, you should have your second derivative is greater than 0. So that's just an overview of inflection points. So now that we've covered all our learning objectives, let's try an exam style question. So let's move on to the exam question. We want to show that f of x, which is equal to 2x to the power 6 minus 6x to the power 5 plus 5x to the power 4 has no inflection points. So feel free to pause the video and try it out for yourself first. So to work out whether we have an inflection point, we want to try and find the second derivative. So if we start with finding the first derivative first, f dash of x, that would just be equal to 12x to the power of 5 minus 30x to the power of 4 plus 20x to the power of 3. And now if we find the second derivative, that would be 60x to the power of 4 minus 120x to the power of 3 plus 60x squared. So now we want to find whether, like, what values of x the second derivative is either large or greater than 0 or equal to 0. So first things first, it'll be useful to factorize. So you would get 60x squared, and that's equal to, and then x squared minus 2x, and then you can simplify, minus 2x plus 1. And then what we want to do is we want to find out if these ones are either less than or equal to 0. So we know that 60x squared, that's always going to be greater than 0 for all values of x. Yeah, but when x is 0, it'll be equal to 0. And then for x squared minus 2x plus 1, So we want to find, firstly, we want to see what the graph will look like. So firstly, we know it will be this U-shaped. And let's see if it crosses the x-axis to see if there's any, it will ever be below. So we can do that by using this discriminant, b squared minus 4ac. So if we do that, we would get minus 2 squared minus 4 times 1 times 1. And that's equal to 4 minus 4, which is just equal to 1. So that means there's only one root of this equation, which is just there's only one real root. So it will only cross there'll be a repeated root, but that means that the graph would be something like this. Like it would only sit on the x-axis, it would never go below. So that means that x squared minus 2x plus 1 is also greater than or equal to 0 for all values of x. So that means that f dash x is also greater than or equal to 0 for all values of x. So that just means that our graph is convex for all values of x. So then we never have a concave bit of our graph. Our second derivative is never equal to 0. So because we don't have a concave and convex part of our graph, it's just convex for all values of x. That just means that our graph, there's no inflection point. So you can say because it's greater than 0, therefore fx is convex for all values of x, so therefore no inflection points. So that's the answer to this question. So remember, you just want to find the second derivative and then see whether it has values of x that when the second derivative is greater than 0 and less than 0. And because we found that it's greater than 0 for all values of x, that means it's convex for all values of x, so therefore there are no inflection points. So thank you everyone, hopefully this was useful and you now understand the second derivative and can use this with context to concave and convex graphs and also points of inflection. So make sure you do loads of practice questions just to make sure you fully consolidate everything we've gone through.